Hello all, welcome to lectures of power system dynamics, and in this lecture I am covering a part 2 of topic power system stabilizers. So let us understand what is going to be outcome for this lecture. So in this lecture you will be understanding what is a concept of dynamic compensator, and we will try to derive power system stabilizer transfer function, and simultaneously our focus is also on the derivation of plant transfer function, that is typically called as GP of S. We are also going to understand what are the relations between power system stabilizer gain and this transfer function GP of S. And at the outset, we are going to summarize what is PSS tuning, and then we are going to understand another two components of power system stabilizer, that is torsional filter and limiter. So let us understand what is dynamic compensator. Dynamic compensator in the control system language is nothing but lead lag compensator. So here you must be observing there are two stages of lead lag compensators are available. But many of the times when in industry, if static exciter is available, only one lead lag stage is adequate. Now, the concept behind this is, as you are aware, in part 1 we have covered, there are main four parts of power system stabilizer. We always start with washout circuit, and then now we are understanding dynamic compensator, and then remaining two parts are over there. One is torsional filter and another is limiter. So out of all those components, the major dominance in the operation of power system stabilizer is from dynamic compensator side. So that is the reason, for design purpose, your power system stabilizer transfer function is always approximated to this dynamic compensator transfer function. So for the design purpose, you can understand power system stabilizer is equivalent to dynamic compensator. But for the sake of testing, means for the sake of checking operational conditions, you have to consider all components, that is washout circuit, dynamic compensator, your torsional filter and limiter. So PSS is always tuned at a particular operating condition. So that is also a concept to understand. So it is not a generalized. You are going to tune the PSS at so particular operating condition, and that is why in power system operation it is always considered as a most critical. So what may be the most critical operations in power system, overall power system? That might be a full load condition with strong or weak AC system. So that is the condition at which your power system stabilizer is always tuned. Now, in this last sentence on this slide, what you can understand is what is typically a purpose of power system stabilizer. So a power system stabilizer is to provide pure damping torque at all frequencies. Ideally, the phase characteristic of power system stabilizer must balance the phase characteristic of overall plant transfer function. So let me tell you the meaning of this GEP. This GEP is typically generator, excitation system and power system. So what is happening in the operation of overall power system? There are main three systems. One is your rotor, another is flux decay, and third one is your excitation system. So whenever signals are passing from one sensor to this power system stabilizer through excitation system, and you are going to damp oscillations, there will be some lag because of these signal transfers, and you are ultimately going to compensate that lag with the help of this lead compensator. But in some of the next points we will understand, if you are going to manage total lag with the help of total lead, there will be some again disadvantages. So this lag is never nullified. So just to avoid some impact of these operations on synchronizing torque. So in next slide, let us discuss what are some important points for this compensating lag, that is how to deal with this lead lag compensator. So the compensated phase lag, now what will be the compensated phase lag? You are having one transfer function which is called as GPS, and you will be having another transfer function which is a power system stabilizer. So it should pass through 90 degree at a frequency around 3.5 hertz. So please understand, when you are studying power system stabilizer, you must take into account that phase and frequency relationship. So on x axis you are having a phase, and on y axis you are having frequency. So this is the requirement just to avoid destabilization of some intraplant modes. So in part 1 we have already understood there are different types of oscillations which are present in the system. So out of that, if you don't do this, there might be some destabilization of intraplant modes with higher frequencies. So just to avoid this is the condition. So this is one of the standard operating procedures when you are dealing with power system stabilizers. Let us understand next condition. The next condition is the compensated phase lag at local mode frequency should be below 45 degree. Now please understand that has not become 0, so it is preferably near 20 degree. So what is the reason behind that? The same which I was discussing earlier. The compensated phase to be lagging at inter area modes, so that PSS provides some synchronizing torque at these frequencies. So in inter area modes, you are required to provide some synchronizing torque with the help of this damping torque. So this is the requirement. And then another concept behind that is you have already undergone through washout circuit, so that washout filter time constant can also affect the compensated phase lag. So this is also the concept. And the third point, the gain of the compensator at high frequencies. Now what will be the gain of the compensator? If you see the transfer function, your gain will be proportional to T1 by T2 into T3 by T4, or T1 T3 by T2 T4. So that should be minimized. The reason is, once if noise enters through this circuit, that noise may be amplified because of overall PSS. So just to avoid that, the gain of compensator should be minimized at higher frequency. So these are some of the important points which you always consider when you are trying to tune power system stabilizer, or you are dealing with these lead lag compensators. Now when you are dealing with lead lag compensators, there are main two what you can say variables we are having in front of us. So these variables have been shown in some of these graphs in front of you. So the two graphs, the variation is in n. So what is n over here? N is nothing but ratio of T1 by T2 or T3 by T4, and your central frequency you can calculate with the help of formula 1 upon 2 pi 1 upon square root of T1 T2. So the observation here from your side must be, when you are increasing your n from 2 to 10 or decreasing your n from 10 to 2, there is variation in the phase. So when you are having higher value of n, you are getting more lead compensation is over there. So that is the motto of showing these two graphs. So you can have a value of n. So another independent variables are, you can independently control this T1, T2, T3, T4, and again ratio of n. So that is also available with you to tune the overall lead lag compensators. Now before going ahead, related with the discussion of this power system stabilizer and lead lag compensator, I would like to draw your attention towards this typical diagram, and this is nothing but diagram of showing overall blocks related with power system stabilizer, not power system stabilizer. This is overall block diagram of power system. So as I had discussed earlier at the start of lecture, so the block diagram of power system is generally represented by three separate blocks. So one of the block is related with rotor dynamics, in which you must observe there are two constants related with rotor dynamics, so K1 and K2. Now if you see the flux decay in this, the constants K3 and K4 will be related, and K5 and K6 will be with excitation system. So this overall block diagram can be divided into three components: rotor dynamics, flux decay, and excitation system. And these K1 to K6 components are typically called as Heffron-Phillips constant in power system analysis. Now this is not the point of discussion for this particular lecture. This will be covered in our lecture series in another lecture, which is called as analysis of synchronous machine. But when you are dealing with your excitation system and power system stabilizers, you may neglect rotor dynamics, because our focus is mainly on voltage and what is the impact of oscillations, and you want to damp these oscillations. So let us, for the sake of time, neglect rotor dynamics. Now here, when you are neglecting rotor dynamics, means you can nullify this constant K1. So how to neglect rotor dynamics? Let us understand some of the important transfer functions related with this. So neglecting rotor dynamics is, you can neglect this constant K1. So how to neglect constant K1 is, there is a typical procedure in industry. When you want to neglect the rotor dynamics, you can calculate this transfer function, which is at the output you are having electrical change in electrical torque, and at input you are going to change Vs, which is nothing but output of PSS, and the condition is your change in velocity must be 0. So I'd like to tell you how this is generally obtained in industry is, you are going to increase the inertia of the generator. So when you are going to increase the inertia of the generator, there will not be any major velocity variation. So in that condition, if you check this transfer function, so for change in Vs, if you check change in T, you will get this GP of S. Now, GP of S is important because depending upon this only you are going to tune the power system stabilizer. This we are going to understand in some of the further slides. So GP of S is again calculated with the help of this block diagram. Like you can obtain this transfer function with the help of standard control system techniques, and again here you can observe, you can express your GP of S with the help of Heparon Philip constant K2, K6, change in terminal voltage and change in power system stabilizer output. So for the sake of understanding equation 3, there is again a big proof of control system. So on this slide, you can observe that this diagram has been modified in some manner, and you can calculate the transfer function. So for the sake of calculating this equation 3, this is the proof for equation 3, you have to draw the block diagram in this manner and you have to calculate the transfer function. So if you calculate this transfer function applying some control system techniques, our motto here is, please understand, our input is delta Vs and our output is delta Vt. So we are interested in calculating or checking the sensitivity of delta Vt with respect to delta Vs. So that is nothing but this transfer function. So K2 by K6 delta Vts by delta Vss. How it is coming? If you try to write down the transfer function, this relationship you will be getting, delta Vt by delta Vss is nothing but equal to Gp of S into K6 by K2 minus K5 omega B divided by this typical uh, rotor dynamics is over there. So once you get this one, simply we are going to comment on what is the value of K5, and then if you neglect this K5, you can calculate GP of S. So what is the GP of S? Then it will be K2 by K6 into delta VTS by delta VSS. So let us comment upon what is the value of K5. So with no load on the generator, K5 is positive and approaches 0 as the transmission system becomes weaker. So for weaker systems, this K5 approaches to 0. This is typically for no load on the generator, and when it is system is under load, your K5 is positive for strong systems but passes through 0 and becomes negative as the system becomes weak. So you can neglect over here K5 because you can neglect rotor dynamics when you are analyzing this overall excitation system and power system stabilizer functions, and then you can calculate GP of S. Now let us understand some of the important comments related with this overall procedure. So how to tune PSS? PSS is to be tuned for a particular system condition that we have understood, which is having highest stabilizer loop gain and greatest phase lag. So these are some of the worst conditions for which you have to tune the PSS. Now, in part 1, we have understood already some of the control signals related with power system stabilizer, and there are some different conditions when we are tuning this power system stabilizer. So, depending upon the control signal, For speed and power input stabilizers, the strongest AC system results in the highest loop gain and greatest phase lag. And for frequency input stabilizers, your highest loop gain occurs when system is weak. So you have to check which control signal you are going to use for overall PSS operation. And at the end, once all these things are done, your gain of PSS is also important, which you can use a standard control system technique related with root locus. So root locus analysis is done for to set the gain of power system stabilizer. Now this overall discussion is around when you are having your input as a speed, but there are some of the things are over there when uh, you are uh, some of the things are not only dependent on speed as a control signal, but you can have some other control signals also, like accelerating power and all. So your earlier block diagrams which are there are not applicable for this analysis. So you have to modify your block diagram when you are using control signal other than your speed. So here this is the modification, and you have to calculate transfer function in a different way. So the two blocks in this figure are important. One is SXS, which is called as a sensitivity block, and another one is a feedback. So with the help of this representation, you can calculate or you can do the treatment of our system stabilizer when you are using control signal other than speed. So let us summarize ultimately how to tune the power system stabilizer. So what we did first, we identified the plant transfer function, so that is called as a GPS. Then choosing the time constant from the phase compensation technique, we had seen that, so T1 by T2 is equal to T3 by T4, and then describe earlier from the knowledge of GPs. So you have to see that earlier some 2-3 conditions we have seen what should be the phase lag, that 45 degree lesser than 45 degree, 20 degree through which it should pass, and all these things once you consider, you have to choose the time constants accordingly, and then you have to select the PSS gain such that it is a fraction of the gain corresponding to instability. So this can be determined from the root locus technique to maximize the damping of the critical modes. So critical modes in the systems are which are least damped. So because they are least damped, you have to damp them more. So these are nothing but critical modes. So this is overall discussion with dynamic compensator, and in next slide let us understand a very simple part which is called as a torsional filter. So in torsional filter is nothing but band stop filter or low pass filter. So some of the torsional frequencies are present in the system, for which you have to take care of. You can go through some of the literature available online. It's a big study, torsional frequencies. So mechanical damages are also over there because of these torsional frequencies present in the power plant. So the major impact on turbine generator system because of these torsional filters, that I have mentioned two impacts. One is there might be a shaft damage to turbine generator because of these frequencies. And even if shaft damage is not there, your power system stabilizer operation will be disturbed because of these torsional frequencies, as your PSS is going to be saturate. So just to avoid this, what should be the design criteria for these torsional filters? The maximum possible change in damping of any torsional mode is less than some fraction of the inherent torsional damping. So this is very standard design criteria. And another thing, you are going to comment on phase lag of the filter also. So the phase lag of the filter is in the frequency range of 1 to 3 hertz is always minimized. So focus band of frequency is 1 to 3 hertz, and you have to minimize the phase lag in this particular band. And last component in your power system stabilizer operation is nothing but limiter. Now why limiter is required over there? Because you can understand sometimes PSS may uh, take some action which is not expected by automatic voltage regulator. As at the start of understanding PSS, we have said that PSS must not operate whenever there is no need. So it should not interference in the operation of AVR should not be there. But sometimes it happens the output of the PSS must be limited to prevent the PSS acting to counter the action of AVR. Now sometimes what happens, the reasons of mal-operation of PSS are, first reason is sometimes load rejection is there. Now when load rejection is over there, AVR must come into the operation, and it has to make its terminal voltage constant. But at the outset, PSS may see it as its requirement of action, and it will take action. So there will be some counter actions from PSS and AVR, and then your mal operation will be there. Another thing is the AVR action is required to maintain the voltage and thus prevent the loss of synchronism after the angular separation has increased. And during this case also, if PSS tries to take some action, your mal operation will be there. So at international level, in one of the power plants internationally, they have developed one typical system which is called as a transient stability excitation control. So some of the characteristics of these are, so drop in the terminal voltage in excess of the preset value, then only the system comes under operation. The second reason may be field voltage is at positive ceiling, and third reason might be a rise in speed above a preset value. So at this slide, I'm declaring that we have discussed totally a theoretical part related with power system stabilizer, and these two parts may give you some direction to study power system stabilizer. But again, I would like to repeat some good contents which are already available um, in internet, or some good books you can use. I would like to repeat those books names. One book is P. Kundur, related with power system stability. Another book is a book by K.R. Padiyar sir, related with power system stability and dynamics. You can go through a link which is showing you how to tune PSS, and that webinar is by PSCAD. In my part 1 lecture, I have given that link to you. And last but not the least, you can definitely go through a course related with power system dynamics, a whole course by a very eminent professor, Professor M. Kulkarni sir from IIT Bombay. And in his lecture series, there is one lecture, lecture number 44, which is telling you about power system stabilizers. So in next part of power system stabilizer, in a very short part, we would like to uh, go through some of the future trends, and what is the state of the art of power system stabilizer, and some of the future trends which are going to be there related with power system stabilizer. Thank you.